Hi, my name is Saket Kenjale, and in today's video we're going to be covering section 1.4, inverse functions. So let's get straight into it. An inverse function reverses the operation done by a particular function. And so now we're going to look at kind of where an inverse function comes from. So we all know that f of x is equal to y. And whenever we create functions, we make sure that our x values are mapped to y. But what if we wanted to map our y values to x? So let's do just that. So right here, this f of x would become y is equal to x to the power of 3 plus 4. But if we want to map our y values to x, then we would have to isolate x. So let's do that. Let's first start by subtracting 4 from both sides. So we would get x cubed is equal to y minus 4. And finally, we have to take the cube root on both sides. And these cancel out, so we're left with x is equal to the cube root of y minus 4. And as you could see over here, x is equal to the inverse function of y. So we could replace this x with f inverse of y is equal to cube root of y minus 4. And what this function is doing is it's basically undoing this original function that we had over here at the beginning. And so this function, which has the property of undoing the original function, is called an inverse function. And another cool thing to note is that if you were to take f inverse of our f of x function of our original function, we would get this. So it would be the cube root, and instead of y this time we're going to put in x cubed plus 4, and then there's a minus 4 at the end. So these 4's cancel out, and we're left with the cube root of x cubed, which is just equal to x. So whenever you take the inverse function of your original function, you will always, no matter what, get an answer of x as your output. So now I'm going to read the definition of an inverse function. So it says, given the function f with domain D and range R, its inverse function, if it exists, is the function f inverse with domain R and range D, such that f inverse of y is equal to x if f of x is equal to y. So in other words, for a function f and its inverse f inverse of f of x is equal to x, like I showed you guys over here, for all x in D, and f of the inverse of y is equal to y for all y in R. So the key things to take away from here is that when you take an inverse of a function, the domain and the range flip. So the domain D and the range R in the original function turns into a domain R and a range D. And another thing to note is that if you were to take the inverse function of the original function, then it will equal x, and if you were to take f of the inverse function, then it will be equal to y. Okay, so now let's look at this figure over here. This figure shows the relationship between the domain and the range of f and f inverse. So for the domain of f, it is the same exact thing as the range of f inverse. And the range of f is the same thing as the domain of f inverse. And so now let's look at our definition of a function. So a function has exactly one output for each input. This is basically the same thing as the vertical line test. And so let's look at a new type of function. It says a function that sends each input to a different output is called a one-to-one function. And this is basically the same thing as saying f of a is not equal to f of b when a is not equal to b. So a good example of a function not following this one-to-one function is a parabola. And this is because if this was -2 and this is 2, and then over here we have 4, look at this. So it says, let's say this is our f of x, and so f of -2 is the same exact thing as f of 2. This is both equal to 4, and they are actually different. -2 is not equal to 2. So this is proof that this parabola x squared is not a one-to-one function. So a good way to know if a function is one-to-one is if it passes the horizontal line test. So a function is one-to-one if and only if every horizontal line intersects the graph of f no more than once. So we could see that if we were to draw a horizontal line across this parabola, it might work for this line over here because it only intersects 0, but any other line it would intersect twice. So that's why this is not a one-to-one function. And something like a cubic function would work because every single time it only intersects one point. So yeah, right here I drew the same thing, but it is a better representation. So this parabola f of x is equal to x squared always intersects between 2 points except for a line down there, and something like a cubic function would intersect only at 1 point. So this is not a one-to-one function, and this is a one-to-one function. So now let's take a look at this example problem over here. So it says for each of the following functions, use the horizontal line test to determine whether it's one-to-one. So this first graph over here, graph A, should be clearly obvious that it is not a one-to-one function, because if you were to draw a horizontal line, it would already cross multiple points, because these are all points and it is crossing them every single time. So that is why A is not one-to-one. If we take a look at B, if we just keep drawing horizontal lines, it is indeed only intersecting through 1 point. And even if we go like this down to the negative quadrants, it is still only intersecting the graph 1 time. So this is a good representation of a one-to-one function. So this is one-to-one, and this is not. This graph A is not a one-to-one function. Now we're going to take a look at how to find a function's inverse. So the first step is to set f of x equal to y. The second step is to interchange the variables x and y. And the third step is to isolate y, and then set y equal to f inverse of x. So let's take a look at this example problem, example 1.29. So it says to find the inverse for the function f of x is equal to 3x minus 4. It wants us to state the domain and range of the inverse function. So let's start by setting f of x equal to y like the first step. So y is equal to 3x minus 4. Now the second step is to interchange the variables x and y. So it's going to become x is equal to 3y minus 4. And now we have to isolate for y, and then set it equal to f inverse of x. So the first step is to add 4 to both sides. This will become x plus 4 is equal to 3y. And then y is equal to x plus 4 over 3. Now we could set this to f inverse of x is equal to x plus 4 over 3. And to find the function's domain, we could see that if we plugged in any number, then it would turn out to be a real number. So that means the domain is all real numbers, or it goes from negative infinity to positive infinity. And the range the same thing applies. So it goes from negative infinity to positive infinity. Any output is going to be a real number. Now, to verify that we actually did find the inverse, it would be a good idea to solve for f inverse of f of x, just to know that it is equal to x. So let's do that. So f inverse of f of x is going to be 3x minus 4 plus 4 all over 3. So these 4's are going to cancel out, and then after that these 3's are going to cancel out, and this is going to end up being x. So this proves that this function over here is actually the inverse of our original function. Now we're going to take a look at graphing inverse functions. So the key takeaway to graphing inverse functions is that the inverse function has to be symmetrical to the original function over the line y is equal to x. So like this, all the way down. And then we just have to copy the opposite function like that. And as you can see, this is what is indicated in the second graph over here. So now let's take a look at example 1.30, and it says, for the graph of f in the following image, sketch a graph of f inverse. So it's always good to start with this y is equal to x line. So it should look something like this. Something like that. And we just want to kind of replicate the opposite of this graph. So it'll look something like this. And I'll go all the way in, and I'll stop at like 2. So something like this. Yeah, something like that. So that is it for this example. Now we're going to look at restricting domains. So the function x squared does not have an inverse function because it isn't 1-to-1. But if we restrict the domain, then it will have an inverse for that interval. So taking a look at these two graphs, we could see that out of this whole parabola of x squared, we only took half of that, and this half is 1-to-1, because if we draw horizontal lines, it will only intersect one point. And the same goes for this other half. So we drew this other half here, and we can see that if we were to draw horizontal lines, it only intersects one point, so that means it is 1-to-1 in that interval. So with this, we are able to create inverse functions of graphs that are not supposed to have inverse functions, basically. So the inverse function would go over y equals x line, so it would go like that. And the same thing applies for this other half of x squared. Just go around like this. So now let's take a look at this example 1.31. It says consider the function f of x is equal to x plus 1, all of that squared. So it says A, sketch the graph of f and use the horizontal line test to show that f is not 1 to 1. Show that f is 1 to 1. So for B, it says show that f is 1 to 1 on the restricted domain -1 to infinity, including -1. Determine the domain and range for the inverse of f on this restricted domain and find the formula for f inverse. Okay, so let's start. That was a lot of information, but let's start with part A. So it says sketch the graph of f. So sketch this graph and use a horizontal line test to show that f is not 1 to 1. So A, we see that the x squared parent function is translated 1 unit to the left. So if this was the parent function, something like that, our function, our f of x, would be over here, and it'll be something like that. So this is our f of x. And if we were to draw a horizontal line through it, we'd notice that it passes through more than one point. So we just proved that this function is not 1 to 1. So now let's take a look at B. It says show that f is 1 to 1 on the restricted domain -1 to infinity. So zooming in on this graph, this is -1. So from this point onwards to the right, all of this graph is going to be included in that interval. This half is going to be included in the interval, and if we use the horizontal line test on this interval, we notice that this function is now 1 to 1. And now it wants us to determine the domain and range for the inverse of f on this restricted domain and find the formula for f inverse. So a smart way to go about it is to solve for the domain and range of this regular function, at least this, and then what we want to do is we want to flip the domain and range, just like this correlation that we saw up here, right here, because the domain and range are flipped for the inverse functions. So by using that logic, the domain for f of x goes from -1 to infinity, and it includes 1. And the range goes from 0, including 0, all the way up to infinity. So if we were to flip the range and the domain, that will be the domain and range for our inverse function. So for f inverse of x, the domain would be the range for the regular function. So that would go from 0 to infinity. And the range would be the domain of our regular function, which is from -1 to infinity, including -1. And now let's find the formula of f inverse. So we know that f of x is equal to x plus 1 squared. So now we set f of x equal to y. Then we interchange the variables x and y, so it'll become x is equal to y plus 1 quantity squared. And then now we could take the square root of both sides, which will leave us with the square root of x is equal to y plus 1. And now y is equal to the square root of x and then plus 1. So this is our inverse function. And to make sure that we got the correct formula for the inverse function, we could check to see if f inverse of f of x is equal to x. And if that's the case, then we have found the correct inverse function. So this is equal to the square root of, then this is x squared, x plus 1 squared. And then we have a plus 1 over here. Alright, well I think I made a mistake over here. This is supposed to be a negative sign. So when we change that back over here, then it actually makes sense. And this would be equal to x plus 1 minus 1, which is equal to x. So this works, and this proves that this is our inverse. Now let's shift our focus to inverse trigonometric functions. So we have 6 basic trig functions which are periodic, and therefore they are not one-to-one. However, if we restrict the interval or restrict the domain where it is one-to-one, then we can define its inverse. So a good example of this is a sine graph. So this is what a sine graph would look like. And you can notice that if we were to test if it's one-to-one via the horizontal line test, we would notice that it does not pass. So if we restrict the domain, like over here, we can see that if we look at the domain from negative pi over 2 all the way to pi over 2, then it is one-to-one. So therefore we could find its inverse. So the domain of sine theta is equal to negative pi over 2 to pi over 2, and they're including negative pi over 2 and including pi over 2. The range goes from negative 1 to 1 and including both of them. We have a similar case with cosine theta. Before, in the sine graph, we had the interval from negative pi over 2 to pi over 2, but with cosine theta we go from 0 all the way to pi, and there we have this one-to-one segment. So these are the graphs of the inverse functions of sine theta and cosine theta. For tan of x, if we look at this segment, it is one-to-one, but we know that tan functions have several of these, and they just keep on going. So if we restrict the domain, in this case from negative pi over 2 to pi over 2, similar to sine's domain, then we could get an f inverse of this. So these are secant, cosecant, and cotangent graphs. And then this is the cotangent graph, this is the cosecant graph, and this is the secant graph. It's important to know that you only need to know this conceptually, and you don't have to very thoroughly understand this concept. And so when evaluating an inverse trigonometric function, the output is the angle. That is an important thing to know. So let's look at this example problem. It says cosine inverse of 1 over 2 is equal to theta. And so we should know that cosine's domain goes from 0 to pi. So that's why it's the theta in this case is pi over 3 or 60 degrees, because we're solving for the angle. So now let's consider a composition of a trigonometric function and its inverse. So for example 1, we have sine inverse of root 2 over 2. And so, well, the longer way to approach this actually is to solve for what's in here, and then after that, or when we get the angle, then we could solve for sine of the angle, and then we will get our value. So if we do that, this would be equal to pi over 4, and then sine of pi over 4 is equal to root 2 over 2. But notice that this ratio in here and this ratio in our answer are the exact same. So the trick is that if we're finding a sine, or sorry, if we're finding a trig function of a trig inverse function of an x angle, then we will get an answer of x. So these two cancel out basically. So this sine and this sine inverse would cancel out, and we would be left with root 2 over 2. And looking at our second example, we notice that it is a little bit different. The sine inverse is outside, and then the sine is inside. When this is the case, then you actually have to do the long method. You have to solve for whatever's in here, and then after that, you have to solve for sine inverse. So in this case, sine of pi is equal to 0, and so this becomes 0. So sine inverse of 0 is also equal to 0. So in this first example, we are finding the angle that makes sine theta root 2 over 2. And in the second example, we're finding the angle that makes sine theta equal to 0. And so the inverse is supposed to undo the original function, but this only works when the inverse function is inside the regular trig function, like I said. So it only works in this case, it only undoes in this case, but it does not undo in this case where the inverse function is outside and the regular function is inside. So now let's take a look at example 1.32, and it says to evaluate each of the following expressions. So first let's go with A. So we know that this is the same exact thing as sine of theta is equal to negative root 3 over 2. And now if we remember our unit circle, we know that at pi over 3, at sine of pi over 3, that is when is equal to root 3 over 2. But notice how this is negative. Sorry, notice how we have a negative sign right here. So that means it could either be in the third or fourth quadrant. But we also have to keep in mind that our domain for sine goes from negative pi over 2 all the way to pi over 2. And it includes both. So because of this, we could say that theta is going to be equal to negative pi over 3. Because negative pi over 3 is in our domain, and it also makes this root 3 over 2 negative. So that is why the answer for A is negative pi over 3. Looking at B, so this was A. Looking at B, it says tan and then tan inverse of negative 1 over root 3. So remembering the trick I talked about earlier, it says the inverse is supposed to undo the original function. And this is the case. Because the inverse function is in the inside and the regular function is at the outside, we are able to cancel them out. And so we're going to be left with negative 1 over root 3. And this can also be written as negative root 3 over 3. Looking at C, this time we can't do the same trick because we notice that our cosine inverse is at the outside. So let's first find cosine of 5 pi over 4. And so when we are at 5 pi over 4, we are we're over here. Because it's pi over 4, 3 pi over 4, 5 pi over 4, and then 7 pi over 4. So this is 5 pi over 4. We have a reference angle of 45. Cosine is negative in this quadrant, and so that's why we're going to have a negative root 2 over 2. So now we have cosine inverse of negative root 2 over 2. And again, we could write this as cosine of theta is equal to negative root 2 over 2. And so we first have to remember cosine's domain, or cosine inverse's domain range. So that would go from 0 to pi. And cosine is negative in the second quadrant, so it would be greater than pi over 2, and it would be right over here. It would be this reference angle of 45, and so theta would be 3 pi over 4. So this is our answer for part C. So now let's look at part D. It is sine inverse of cosine of 2 pi over 3. So if I were to locate 2 pi over 3, this would be pi over 3, and this would be 2 pi over 3. And we would have a reference angle of 60 degrees. And cosine is negative in the second quadrant, so we're going to have a negative value, and then since the reference angle is 60 degrees or pi over 3, cosine of 2 pi over 3 is going to be negative 1/2. So now we're going to have sine inverse of negative 1/2. And again, this is the same thing as saying sine of theta is equal to negative 1/2. And so if we were to draw a graph, sine theta would equal 1/2 when we have a reference angle of 30 degrees or pi over 6. But then we need a negative 1/2, so we could go down to the fourth quadrant and have a negative 30 degrees or a negative pi over 6. And so that is why our theta, or our answer, is going to be equal to negative pi over 6. And by the way, we have to go down instead of going around like this, or even around all the way up over here, because of the fact that it does not fit in our domain. This is going to be 11 pi over 6. This is going to be 7 pi over 6. So they won't fit in our domain of, just to remind you, won't fit in our domain of negative pi over 2 to pi over 2. So that's why we have to go down to negative pi over 6, because that is in our domain. And so that's why negative pi over 6 is our answer. So this is going to be it for section 1.4 inverse functions, and I hope you'll join me in the next video, section 1.5, where we will look at exponential and logarithmic functions. I'll see you there.